answer your question. So what we are going to learn today are basically two theorems, divergence theorem and Stokes theorem. How many of you know about divergence theorem? Can you raise your hand? Divergence theorem. How many of you know about it? Okay. Okay. So less than half. So if you know divergence theorem, you probably also know about the Stokes theorem too, right? How many of you know about Stokes theorem? Okay, the same guys are raising their hands. Okay, good, good. So yeah, so for those who already know what divergence theorem and Stokes theorem are, this lecture probably too easy, but I'll try to be as comprehensive as possible for those who never heard of this theorem. So divergence theorem states like this. Okay, so you have a vector field A, and then you have a closed, you have a closed surface S, right? And the volume enclosed by this surface is V. So this V is this, and then this S is this, okay? And then of course, A, the vector field can be defined everywhere, right? At each point in space-time. Now, if you perform this flux integration, like if you add up the vector flux passing through the surface, which is this, is equal to the volume integration of divergence of A inside this volume. Okay. So I'm not sure how strange this statement sounds like, but to me, this is actually very interesting, because what this basically says that you can know the result of the volume integration without knowing anything about the volume, without anything, any information about the inside, right? Because this is equal to this. So just by performing the surface integration, you know the result of the volume integration, right? To me, that sounds actually pretty strange, right? Because, you know, by performing the surface integration, you know, the result of the volume integration. And the proof is actually pretty simple if you know the definition of the divergence. So the definition of divergence was like this: limit delta V goes to 0, delta V A dot ds, right? So this was the definition of divergence of A. So now we can imagine the situation that your volume is divided into many cubes. Okay, many cubes. And then you just enlarge this region into this. So basically this one is your outer boundary, and then this is inside, right? And then you have multiple, like millions of cubes. So for each cube, you can apply this definition. So so just to make things easy, you can just move this term into here, delta V. Okay, then this is equal to this, right? So the divergence of A dV is equal to summation of A ds for all surfaces, because the summation, like we are assuming a cube, so this integration can be written like this, right? Summation of all surfaces, right? So adding these up is basically you're adding this value for this cube, that cube, this cube, and so on. So now let's think about these two cubes. Let's say I'll say this is cube 1 and cube 2. And then these two cubes shares a one surface, right? This surface is shared by cube 1 and cube 2. And then if you think about this value, a dot ds, in the perspective of cube 1, this surface has direction to right? Because it's always outward direction. And then in the perspective of cube 2, this surface has direction to the left, right? So the a dot ds magnitude are basically the same, but depending on the perspective, they have different sign because they have opposite direction. So if you add them up, they actually cancel each other out. So you have zero contribution. And then this thing happens again and again. Like let's say you now want to add this one to this cube 3. And cube 3 and cube 1 shares this interface, right? And the same thing happens. The contribution from this interface is just canceled out. And same thing happens again and again and again. So the contribution from the inside surfaces are all canceled out, right? And then you have only the contributions from the outer surface where there's nothing you can cancel with, right? So this integration, volume integration, is equal to the surface integration. And then here, this surface is the outer boundary of the volume, right? So this is the divergence theorem, which is convenient in many occasions. Okay, and then this is actually also called Gauss theorem, and you will know why later in the class. So, any questions so far? Is this theorem or proof is clear enough, or you have anything you want to further clarify? So the idea is simple, right? You just you have a volume, and then you cut the volume into multiple cubes, and then if you consider these two cubes, which are sharing one interface, the direction of the interface are exactly opposite depending on which cube you are looking at, right? So that they cancel each other out, right? So interface, the internal surface contributions are just zero. Okay, Park Jun asks, we have a limit delta V equals to 0 for the definition of the divergence. In the proof, are we ignoring that limit? Yeah, this is a good question. And you can just assume that we dissect these volume into very, very, very small pieces so that this limitation, this limiting behavior is been already taken into account. Yes. Is there any other thing? Any other question? So the proof is pretty easy, but the meaning, I think, the real meaning of the divergence theorem is, again, by simply performing the surface integration. So all you know is the information about the surface. Then you can get the information about what's inside. That's kind of a interesting thing about this divergence theorem. Okay, so if there's no other question, let's just move on. The second one is Stokes theorem. And as you can see, it looks very, very similar to divergence theorem. So now on the left-hand side, you have line integral. And then right-hand side, you have surface integral, right? And then you have a curl here instead of a divergence. Okay, so this is Stokes theorem. So if you have any surface S, and then the curl, if you perform a curl of A dot ds surface integration, the result is going to be same as the result that you perform a line integration of the boundary. So it's basically the same thing. It's just a one dimension, you know. Now this is just one dimensional integral, and this becomes a two dimensional integral. And previously it was 2 to 3, right? And then the proof is also pretty similar. So if you think about definition of curl of A, it's like a limit delta S goes to 0, delta S, and what was it? A dot dl. Of course, you have this sign thing. I'm sorry, direction thing. So same thing applies here. If you want to add this curl of A dot ds for each loop, like sub loop, then let's say this one loop 1 and loop 2 shares this line segment. And then this line segment, the positive direction for path integral is downward for the perspective of loop 1, right? Because loop 1 wants to take integral like this. And then loop 2 also wants to integral like that, so that this line segment, the positive direction for line integration is upward, right? So A dot dl have the same value for loop 1 and loop 2, but they have opposite sign because of the opposite direction. So they cancel each other out in terms of contribution. And then same thing happens over and over for neighboring loops. And then the contribution from inside just cancel each other out. And then I think this figure, it looks pretty very intuitive. So if you look at this, all the outer surfaces, you have only one arrow going this way. Okay, so the contribution of the line integration of the outer boundary survives. But if you look at the inside always have two contributions. One going up, one going down, right? Because you have two neighboring surfaces. And then these contributions cancel each other out, right? So everything inside is not added, and everything outside is going to be added. So that's how Stokes theorem works. So is that easy enough? Like how do you feel? I guess this is not too difficult, right? It's just a similar thing, like Stokes theorem and divergence theorems are the similar things, and then even the proofs are similar. So I guess you have no problem understanding this. Okay, Hwang Jinung says, does S have to be open surface? This is a interesting question. Usually people use Stokes theorem only for on the open surface, right? So that you can clearly define the boundary. But for the closed surface, I don't see any reason why you cannot apply this. So it's gonna work. And then if that's the case, then there's no boundary, right? So your boundary is in, like, you can think about this type of a surface. Say like this. So you basically have some like sphere-like surface with a small hole here, right? Then the boundary is this small hole, right? And then eventually, if it becomes a closed surface, your boundary disappears, right? So if that's the case, I guess this integration must go 0. Yeah, I have to check, but I guess that's the case. But this is really good question, really interesting thing to think about. Okay, so Fakri asks, well, I don't get why the left and right sides of the theorem equation should be equal. Our proof only includes why we should look at outer boundaries and ignore interior. Right. And then if you understand that we can only take into account the outer boundaries, then you can just go ahead and basically conclude the last line of this proof, which is equal to this, right? So what this tells you is that, like, if you, so curl of A dot ds, the integration of the curl of A dot ds is equal to the summation of A dot dl for all outer boundaries. So summation of A dot dl for all outer boundary is equivalent to this, right? And then summation of curl of A dot ds for all inside is equivalent to that. So I think it's kind of straightforward, like from here to here. But let me know if I miss your point. Probably I misunderstand what you said. Okay, and An Donghyun asks, okay, so An Donghyun asks if this theorem applies to higher dimensions, like not like 3-dimensional space, but let's say we have an n-dimensional vector space, then how does theorem changes? This is also an interesting question. And then, of course, there is a general way to generalize this theorem into like a multi-dimensional space with n larger than 3. But I don't have the answer right now because yeah. So, but you can always check, mathematical textbook, okay, and you can get the answer. So the reason why we do not cover that, like even higher dimensional space, is because we are doing physics rather than mathematics now. So what we need is 3-dimensional space, right? But obviously you can expand this result into multi-dimensional spaces. And then I think you can just check just by checking at mathematical textbooks. But this is a good question, though. I just don't have how exactly can we expand this into multidimensional space. That's a good question. Anything else? Okay. Okay, so that's very nice. And let's move on. So usage in physics, it's just about the equivalence relation. So we can use divergence theorem and Stokes theorem by relating the derivative form of Maxwell's equation to integral form of Maxwell's equations. So Maxwell's equations are these 4 equations, right? Divergence of D is rho f, and then divergence of B is 0, which means now just by looking at it, you should be able to kind of imagine how your vector field behaves. So this means you have some rho f, which is your source, right? And then depending on your rho f amount, you can obtain your D field or electric field in diverging manner, right? So this is about divergence of D is rho f, and then divergence of B is 0, means there's no magnetic charges. And then there's two other equations. Curl of E is equal to minus dB dt. So if you have a time varying magnetic field, so if your magnetic field changes as a function of time, then that can create electric field in a rotating manner. So if you have, let's say you have a magnetic field, and then the amount of magnetic field changes as a function of time, up and down and up and down, then your electric field is going to be created like this, right? In a rotating manner. And similarly, here, curl of H is equal to JF, which is current, plus dD dt. So if you have a time varying electric field, it can also create magnetic field in rotating manner, right? So you should be able to now understand the equation, can kind of imagine how the electric field and magnetic field is going to behave based on these equations, right? Of course, you're going to learn like how can you interpret these equations in more rigorous manner as you learn more about electromagnetism, but this is basic kind of thing that you should be able to do. Okay, now you have 4 equations, and then you can relate these 4 equations with integral equations. So what you do is you take volume integral on both sides. And then this side is just the same, but this side, by divergence theorem, can be changed to surface integral, right? And then similarly, you can do the same thing for here. And the Stokes theorem, by performing the surface integral, the left-hand side becomes a line integral, right? Right-hand side stays the surface integral. So the relation between the differential form and the integral form of Maxwell's equation can be simplified using divergence theorem and Stokes theorem. I don't want to go into too much of a detail, like too much of a physics interpretation here, because we are going to do it anyway in the following lectures. But for now, you can just think that this is the usage of divergence and Stokes theorem. So any question regarding this slide? Okay, so if you have anything, you can just type in the question, type in the chat box. I'll go back and try to answer. This is actually, but before we talk about this painting by Escher, I want to talk a little more about this thing first, what's written in the bottom first. So there was one question in the last lecture asking that why we have only electric scalar potential, right? Why there's no magnetic scalar potential. So that question was like this: U gradient of U minus gradient of U is E, right? And then U here is a scalar potential. And then as we said, it's very, very useful because E, electric field, is a vector field. So it has 3 components, difficult to handle, but u is a scalar, so it's much easier to manipulate, I mean, play around. So it's very useful to express E as a gradient of some scalar function. But when we say B is typically written as a curl of A, okay? And we call this A as a vector potential, right? And then vector potential is less useful compared to scalar potential, because anyway, both of these have three-dimensional thing or three-dimensional thing. So both of these requires three numbers to define, right? There's not much of a simplification in terms of arithmetics. But why? Like, is this inevitable, or like, is there any way that we can like say B is a gradient of something, some scalar function? So here's a short answer of why this is the case. So for irrotational field, like curl of A is 0, okay? Then by Stokes theorem, the line integration of A dot dl must be 0, right? So from here to here, I think everyone is pretty clear, right? By Stokes theorem, this is trivial. And can you relate this property and that property? So in other words, like the line integral of a closed path of vector A is always 0. This property and the possibility that we can describe A as a gradient of a scalar potential, these two are actually related. How many of you understand these are related? How many of you catch that these are related? Please raise your hand if you catch like these are related. Okay, there are very few, like just probably less than 5 people understands. So we sometimes also call this as a conservative properties. Okay. So why these are related? Let me explain. So let's say you have a point A and point B in space. Okay. And then you want to evaluate. So if you have a point A and point B in the space, then you should be able to define your scalar potential in a unique value, right? So for instance, let's say VA is some value, and then VB must be some value, right? Some unique value, I'm sorry, some unique value. And now, sorry, A and B. Now let's think about the line integration. So let's say you want to, you follow this line from A to B to integrate your vector field A, okay? So vector field A to B dl, okay? Let's say this is some value. And then that value must be same as delta V, right? The potential difference between these two. And then think about you perform this line integral for some other path, okay? Then, and so let's say this is path 1 and this is path 2. So let's say path 1 and then A to B, path 2, A dot dl, right? So in order to be able to define your scalar function, these two must be the same, right? In other words, your path integral shouldn't depend on which path you choose. It should only depend on the initial point and the final point, right? It should not depend on the path, the specific path you choose, right? So that's a critical thing that you need in order to define the scalar potential. And then how this is related with that? That is because if you take the opposite path, so the inverse of the path 2, then this becomes B to A, right, along path 2. And the value is exactly same as negative of A to B path 2 A dot dl, right? So now you connect path 1 and path 2. So from A to B along path 1, from B to A along path 2, and you get the original position. And then you must, in this round trip, you must have a 0 line integral, right? And then that guarantees that this integration and that integration are basically the same value, right? So what I'm saying is that this guarantees your line integral only depends on the initial point and final point and does not depend on which specific path you choose, right? And then that is necessary condition to have this. So is that clear? Please ask if there's any question related with this. And then, so you can type in the question while I'm keep explaining things. So the solenoidal field, divergence of A is 0. From here to here, you can apply divergence theorem, right? So the surface integration of the flux is 0. And then in this case, you can explain, you can write your vector field as a curl of some other vector. Okay, but in general, if your vector is not irrotational or not solenoidal, then you can express your vector as a linear combination of gradient of a scalar potential and the curl of a vector potential. So this is general form. Okay, and in these two special cases where your vector has irrotational property, you can express your vector as a gradient of a scalar function. And then if your vector field is solenoidal, then your vector field is written as a curl of some other vector. So now, going back to your question, why only electric field can do that? Okay, so first of all, why magnetic field can be written as a vector potential, curl of vector potential? That is because of this, right? So magnetic field is the divergence of a magnetic field here is 0, right? So because of this, it is guaranteed that you can express B as a curl of some vector potential. Okay, and similarly, if you look at this equation, your electric field is divergence of your electric field is not 0. It's not guaranteed, right? So you cannot explain your electric field or E field or D field as curl of something, right? Because it's non-zero. Now, if you look at this equation, you can make your curl of E 0 when there is no magnetic field or there's no change in magnetic field, right? And we can call this as an electrostatic condition. So in electrostatic condition, where your curl of E is 0, you can express your electric field as a gradient of a scalar potential. And this is only possible for electrostatic case, as I said earlier. So in general, as I said, dB dt can be non-zero, right? In this case, you cannot express your electric field as a gradient of V. So this is only possible for electrostatic case. Okay. But the curl of B can be written as a curl of A always without any condition because it's kind of guaranteed by Maxwell's equations. Okay, so I think this could be an answer for your question, but please ask if there's anything unclear. Oh, by the way, the reason I brought up these figures is because this reminds me a very nice memory about my undergraduate age. So when I was a sophomore, yeah, I think I was sophomore, I took art history class or 미술사. And then the final project of this class was pick one artist and then kind of interpret their artwork in a new perspective. So I took this guy, Escher, and then Escher's paintings are always like this, like impossible things. Like if you look at this thing, these guys are moving upward, right? And then if you go also here, also moving upward, move up, and then from here to here, they are also moving up, right? So it's just keep going up and up and up and up, which is impossible. And then here, if you look at this too, if you follow this line, okay, reasonable, reasonable, going down, reasonable, reasonable, and then there's a waterfall, okay, which means it just keeps going down forever, right? So if somebody asks you, what's the height or altitude of this position, then your answer should be changed because like how many turns you go, depending on how many turns you run, your height is gonna be changed, right? Because it's keep going up and up and up and up. So there's no way that you can define a single value altitude here. So I interpret this as a non-conservative force, like in art history class. And the professor really liked it. I mean, I explained that, okay, in physics, there is what is called conservative and non-conservative force. Conservative force means if you take a line integral here, you have to get 0. But if you look at here, it's keep going up, which means if you take a line integral, it's a positive value. So if you, depending on how many turns you go, it keep added up. So it's non-conservative force. So it's kind of a artistic representation of non-conservative force. And then he really liked it. And then I got A+. So this is actually a really nice memory for me. So I also want you to leave some impression about, just when you hear about like conservative force or irrotational field, just think about this figure, okay? And then you need to have line integral to be 0 for the closed path in order to define scalar potential. these are kind of necessary conditions. Otherwise, like if you take a line integral and then it's non-zero, then you cannot define a single value scalar potential. Okay, so Park Jun asks, so based on what I understood, there isn't necessarily a derivation of A equals negative gradient of V based off of line integral of A is 0. The argument goes that for the line integral of A to be 0 across any closed path, A must necessarily be the gradient of a scalar potential. However, I'm not entirely sure why the 0 line integral means that A has a scalar potential. Okay, so this is actually a nice question. So what he pointed out is my kind of an explanation why these two quantities or these two relations are related. It's not like complete, right? I didn't explain like, as a matter of fact, these two are kind of if and only if condition, but I only explained just one direction, and even that was not complete. I just gave you some impression why, you know, this is kind of related. So what Park Jun pointed out is correct, and the reason why I did that is I thought that this is kind of enough for this class. But of course, there's a rigorous proof, and you can easily find it in a Wikipedia even, because it's kind of elementary thing. So I recommend to try to look at those. I mean, it'll be much better for you, like to follow like rigorous mathematics instead of just explaining things in words. But explaining things in words sometimes is much more powerful than just reading the full mathematical proof, because you can get some sense, and I want to convey some sense. That's kind of my goal in this class. But this is really good question. Yeah, and you're right. My explanation was not a proof, right? And also, there's another condition here too. Like I just said that any A can be written as a linear combination of a gradient of V plus curl of F. But this is also not true, strictly speaking, because A has to satisfy certain condition. And that certain condition is this: any sufficiently smooth and rapidly changing vector field. Okay. And then for those who are majoring in mathematics, this statement is very, very vague, right? What is sufficiently smooth? What is rapidly decaying, right? It's kind of very loosely defined. And then, of course, there is a strict mathematical definition of how sufficiently smooth and how rapidly decaying. But I just want to leave it as your homework. If you're interested, you can just check it. And then otherwise, just leave it. Because it's kind of, I think, a rigorous definition sometimes make your life unnecessarily complicated. So I just want to give you the core thing. Okay, and any other question? By the way, don't get me wrong. I'm not saying that mathematical proofs are meaningless, right? The mathematical proofs are very important, but for some people, sometimes it's good enough to know how things are going instead of learning everything rigorously. Any other question? Okay. Good. So if there's no question, I think I can move on to the next lecture note. Oh, there's one more. Okay. So yeah, so this is nothing. This is just I just wrote some useful vector identities, and this is just good to check.